In the previous video we looked at the forces that existed on currents in magnetic fields. We're now going to have a look at what happens when we have individual charges moving through magnetic fields. And to do that we're going to consider that a current consists of a whole heap of charges, and all of those charges are moving. So instead of considering all of them at once, we're now going to look at each individual charge and identify the force that's acting on it. So by considering them separately, we're not worrying so much about the conductor as a whole, we're worried about an individual charge. So this situation is not too dissimilar to what we were looking at previously. So again, if we've got these magnetic field lines directed upwards, instead of representing the current, we're now going to represent a single charge, and in this case we'll identify that it's a positive charge. So it's going to be moving in this direction, and the quantity that we need to identify now is its velocity. So if we go back to the equation that we saw previously, we had that the force on a current was given by BIL sine theta. Now, we're not interested so much in the current here, we're interested more in that charge. So we can break that expression for current down into Q over T. So current being the rate of flow of charge, so we can make that substitution instead. Now, I'm going to just rearrange this slightly, and we're going to take the Q out of that and replace it with the L. So we're going to have L over T multiplied by sine theta. Now L is just a distance that the charge is moving through the field, and so we've got a distance over time there. So we now have that the equation is given by BQV sine theta. So that's the same idea as the previous equation that we saw for current, except that now we have F being the force, B is still the magnetic field strength, we now have the charge, so the charge Q, where it's going to be measured in coulombs, and V is the velocity of that charge, and that will be in meters per second. And we still have that angle theta, which is now the angle between the velocity and the magnetic field. If we consider the direction for that force, we need to be aware of the charge that we're dealing with. So we can identify that if it's the same charge as conventional current, so in other words, if we're looking at positive charges, that means that we're still going to see that same direction of the force. So we can still use the right-hand palm rule. However, if it's a negative charge, that means it's going to be in the opposite direction, and there's a few ways that you could think through this. The first is that you just consider the right-hand palm rule for positive charges and then reverse that direction to get what it is for negative charges. You could, if you wanted to, I guess, go with the left-hand palm rule. So use your left hand for negative charges, right hand for positive. Another alternative would be the right backhand rule. So your palm indicating the direction for positive charges, the back of your hand being the direction for negative charges. Now there's one key difference between charges and currents. That's that with currents, all of those charges are constrained within the conductor itself. So they can't really move around anywhere. They can only move in the direction that the conductor itself allows. But a charge moving by itself can actually change direction. And in this case, the force will actually change the direction of the velocity because there's nothing stopping it from moving in any direction. And so the velocity vector is actually going to change direction, and that will then mean that the force and the velocity are always going to be perpendicular. And that's because as the velocity starts to change direction, if you wanted to figure out the direction of the force, you would then need to readjust your hand using the right hand palm rule, and as a result the force will always be perpendicular to that direction of the velocity. And this is actually the condition for circular motion. That is, that the velocity vector and the force vector are always perpendicular. So that means that the motion of a charged particle in a magnetic field is always going to travel in a circular path. So that means that we can then use the equations for circular motion to determine a few other quantities, such as the mass of the object that is charged. So to explain that just with a diagram, let's imagine now we have the magnetic field directed away from us, so into the screen. We're going to have a charge plus Q, so we'll keep it positive so we can still apply the right hand palm rule, and that's going to be moving in towards that field with a velocity v. And using the right hand palm rule, we can see that fingers are directed into the screen, thumb pointing to the right. That means that the charge is going to experience a force that pushes it up the page, and so that means that it's going to start to curve in this sort of manner. Now, depending on how fast it's moving, the strength of the field, and so on and so forth, that's going to determine how much of a curve it has. So we could then identify that there is a radius of curvature for that circular path, and that then allows us to figure out some other quantities associated with this charge. So that's the detail for moving charges in magnetic fields. We'll have a look at a few problems in class to make more sense of that, and have a look at a couple of applications of those ideas as well.